Good morning, sir.
Hello, good morning.
I'm just helping out. Just other people have to enter. So I will be leaving and checking the other tutorial where Devishottam has to join.
Okay, no issue.
Please stay here for the others.
Yeah, sure. I will be here.
I'm just reiterating the reason you need to be here is otherwise the meeting will end for all.
Yeah, I will be here.
Okay, thank you. Thank you. Shashiji, are you in touch with Professor Gugan Thope?
No.
Would you be calling?
No. This session is being taken by me, so I'll be.
Okay. Thank you, sir. Sorry about the inconvenience.
Shall I share the screen?
Yeah, I mean, if you have a holding slide, you can share it, but we will start at 11:30 sharp.
Yeah, no problem. That's okay.
Thank you.
Yeah. Okay, so shall I get started?
Yes, sir. Yes, please.
Okay, thank you. So, good morning, all of you. My name is Shala Bhatnagar. So, what I'll be talking about during the course of today's lecture as well as tomorrow's lecture is to give you some idea about foundations of reinforcement learning. And this is roughly one slide summary of what I am going to do. I'll be focusing a lot on the foundations, essentially on reinforcement learning, and it turns out that reinforcement learning derives a lot from what we call as Markov decision processes. And then we'll be talking about numerical techniques as well as simulation based algorithms and so on. So here is a one slide primer on what RL is all about. Essentially, you have an agent that is represented by this circular object, and that is interacting with what we call as an environment, which is this rectangle. And the environment can be in one of several states that are represented by these small circles. And let's say the state of the environment at time n is Sn, which is this small circle. And then what the agent does is it looks at the state of the environment, and the job of the agent is to pick an action or a control. So let's say that the agent picks this action an at time n. And then the environment does a couple of things. It gives the agent a reward, let's call it as Rn. And at the same time, it transitions into another state. And this transition is somewhat probabilistic in general. So that it depends. Okay, so from the state Sn, it jumps into some state Sn plus 1 probabilistically. And then the agent looks at the reward, and basically what the agent does is then it looks also at the state and takes another action, an plus 1, then the environment repeats the same thing, gives another reward to the agent, and sort of jumps into another state probabilistically. And this process is repeated. One might be wondering as to what is the ultimate goal here. There are various ways in which the goal can be specified. But ultimately, the notion, there is something called as a long-term reward, I mean, which you can, of course, describe differently in very different settings. And the job of the agent, is to maximize the long-term reward via this choice of actions depending on the states of the environment. At the bottom of this slide, you will find a few references. There's this book of Sutton and Bartow, which is like an elementary reference, which actually gives a lot of intuition and detail, but not so much of mathematics. This is, and they have revised it. This includes a lot of new material as well. This appeared in 2018. And then there's this new book by Dimitri Burtsikas on reinforcement learning and optimal control. This appeared just in 2019. And then there's this popular book again by Burtsikas and Tsitsiklis on neurodynamic programming. This appeared again in 1996. So it turns out that reinforcement learning, as I said, has close connections with what we call as Markov decision processes. So by Markov decision process, so we essentially mean a controlled random process. Let's call that a sequence ST. And in turn, this depends on a control valued sequence. Let's call that a sequence AT. And it satisfies what we call as a controlled Markov property, which I'll describe on the next slide. Now, the set in which this ST random variables take values in is, let's denote that as capital S, and this is called the state space. Okay, this in general is these. We call ST as the state at time t, and so that's what it is called. And capital A is the action space, is the set of all actions, from where the agent can select. And in this talk, we'll just assume that, for the most part of it, we'll assume that S and A are finite sets. And in general, when the state is I, there's a set of feasible actions. Let's call that as A of I. The point is that not every action will be feasible in every state. So you can identify with every state a feasible set of actions. So let's call that as A of I. And in general, you can see that A, which is the set of all actions, would be the union over I in S of A of I. Now let's denote as K of ST, AT, ST plus 1. This is the cost, is what we also call as a single stage cost that is incurred, when the state is ST, let's say, and the action chosen is AT. So here is sort of the timeline. So at time t, the system is in state ST, the agent selects an action AT. And then at the next instant, so we are assuming, of course, that time is discrete for convenience. And so at time t plus 1, the state is then in ST plus 1. And what is received by the agent is this cost. Okay, this check is what the agent receives, and this is what it needs to pay. K of ST, AT, ST plus 1. So it depends on the state ST at time t, the action as also, and also the next state in general. Many times one can ignore this next state as well, but that can be derived as a special case of this more general setting. This part, I mean, if you are interested in Markov decision theory to learn in more detail, there's this book by Martin Butterman, 1994 volume. It contains a whole lot of detail on various settings of Markov decision process and a lot of results and so on. And there's this more recent books by Dmitry Burtsekas on dynamic programming and optimal control, 2017. These are like the latest editions of it's been revised multiple times. So in this talk, I'll be taking a lot of material from Burtsekas' book, some material from the book of Burtsekas and Tsitsiklis, and also some material from Sutton's book. So I told you there's something called as a controlled Markov property. So what it means is the following. It's you can view it as a generalization of the Markov property. And what it says is that, suppose I I ask this question: what is the probability that the state at time t plus 1 is S prime, some point S prime within the set S, given that the state at time t is S, the action that you choose at time t is A, and I give this entire history of states and actions that I have chosen starting from time 0. Then if it just turns out that it depends merely on these two quantities, so that the state at time t is S and the action at time t is A, it does not really depend on how you arrived. So that's what this figure is trying to indicate. So as long as I know that at time n I am in state Sn, and the agent has chosen this action An, now how you arrived in that this state Sn is immaterial. As long as you select, that you are in state Sn and you select An, the next state will depend only on these two quantities, not on how you actually arrived. So that's basically the controlled Markov property. So in a so I told you there's something called as a long-term objective. That's what the agent is trying to optimize. There are various ways in which the long-term objective can be characterized. One of these is, of course, what we call as a finite horizon problem. So the idea here is that the agent is going to be selecting actions only over a finite amount of time. I mean, and that is a given quantity. So it could be useful, for instance, if you are, let's say, a startup company, or maybe a manager of a firm, or you want to set up a company, let's say, something like that, and then you need to decide how long, what is your vision? I mean, how long you want your company to be? I mean, initial guess, what's your estimate? How long will this last? So let's say you say, okay, my idea is that I'll set this company up for 20 years, and I want to maximize my profits during this 20-year window. So you're not really looking at anything beyond 20 years. So you are focused on that. Okay, so the goal here is that, so the point is that the horizon length is something that is given, it's fixed. It's let's call it as capital N. And then we need to set up this problem wherein you would like to find the optimal sequence of actions given the states of the environment at various times that actually minimize your cost objective. And when we talk of MDPs, it's more natural to talk in terms of costs. In the reinforcement learning setting, it's more natural to talk in terms of rewards. I mean, but of course, mathematically, you can see that both of them are analogous. I mean, the optimal policy that one gives would be completely analogous to the optimal policy the other setting would give. So I'll herein concentrate on the cost setting, which is more natural to Markov decision process. So we'll call an admissible policy phi has a sequence of functions, and this is a sequence of n functions. Okay, so n again is related to this. So n is the horizon length. Okay, so let's call this as these functions as mu0, mu1 up to mu(n minus 1). These are these n functions. So the idea is that these are all functions that map states to the actions, and these should be done logically, so that in a state, if you are given a state, you should only be picking actions from the set of feasible actions or actions that are feasible in that particular state. Okay, so that's what it is. But then the idea is, why do we need these n mappings? The idea is that at time 0, you will be picking actions according to this mapping mu0. At time 1, you will be picking actions according to mu1. At time n minus 1, you will be picking actions according to mu(n minus 1). At time n, the horizon ends. There's nothing for you to do. I mean, you just record the state where you terminate, and that's the end of it. So actions are chosen only at these instants, 0, 1, 2, up to n minus 1. Okay, so that's what it is. So let's assume that capital pi is the set of all admissible policies. And the objective is to find a pi star, which is like the optimal policy is what we call it, that minimizes this kind of a cost structure. So we'll denote by j pi of I, pi again because this pi is this pi policy. That's the subscript here. I denotes the state. And this is the expected value of this entire sum. So what is this sum? This is the sum of all single stage costs that you encounter during the course of the evolution of your process. So at time 0, suppose you are in state I. So we are conditioning on this fact. The time 0, the process was in state I. And then, we picked action mu0 of x0, which is coming according to this policy pi, which is why this is subscripted by pi. And then, you incur this cost, which is k of x0, mu0 of x0, comma x1. And then the process jumped probabilistically into x1 state. Now at x1, you pick action as mu1 of x1, and then you move probabilistically into a state x2 and so on. So you can see that there's just a sum of costs. And this is what we call as a terminal cost, h of xn. Okay, so xn is like the terminal state, the state in which the process ends. And there is a cost associated with that as well. Okay, you can, so that's what it is. So the expectation here is, of course, over the entire sequence of states that you are going to visit from time 1 onwards until time n. So that's what j pi of I is. And then the goal is to find a policy pi star that minimizes j pi of I over all pi. Capital pi, again, as I said, is the set of all admissible policies. So let's call this as j star of I. So the goal is then to find j star of I. Okay, and then also to find the pi star, which is this policy that we call as the optimal policy that attains this optimal cost. So as far as this finite horizon problem is concerned, this is what it is. Now there's this this principle called the principle of optimality. What it says is the following: that let's say that pi star is your optimal policy, and let's say that when we are using pi star, let's assume that we encounter a state xi at time I with a positive probability. And now what we'll do is we'll consider a subproblem, which is to minimize from time I to time n. Instead of going from 0 to n, we are now going from I to n of this entire exactly the same structure, except that we are summing from I to n. Okay, so that's what this subproblem would be. And so let's say we want to minimize overall policies over all these truncated policies. So then it turns out that if you just truncate this policy, the optimal policy, you look at this tail sub policy, which is mu I star, mu I plus 1 star up to mu n minus 1 star, again obtained from here. That should be optimal for this subproblem. Okay. Now the point is that if it was not optimal, then you could do the following. Suppose you are able to find another policy that was optimal. And quite clearly, whenever you reach state xi at time I, you start using that policy, and then it would turn out that if you append that tail policy to this, to the initial portion of this policy, that would be optimal. But then that's a contradiction to the fact that this is an optimal policy to begin with for the original problem. Okay, so it's clear then that this is going to be an optimal policy for this subproblem. Okay, so this gives us something. This tells us that this gives us a way of constructing an optimal policy. What it tells us is that you can construct an optimal policy by going backwards in time, which essentially means you construct the optimal policy for the tail subproblem involving just the last stage n minus 1. So look at the cost incurred in stage n minus 1 and the terminal cost. Just start from there. And then go 2 steps back and so on until the full optimal policy is constructed. And that's what this algorithm that is called as a dynamic programming algorithm gives us. So what it tells us is this is this algorithm, okay, that is represented by these couple of equations. So it says that for every initial state, let's say I naught, the optimal cost, J star of I naught of the basic problem equals J0 of I0 that is obtained from this algorithm. Okay, so what does this algorithm do? What it does is it computes a sequence of functions. So it computes Jn of in, which is like the terminal cost function. It just assigns the terminal cost. So if your state is in at time n, that's the terminal state, then the cost incurred is h of in. So it just assigns Jn of in as h of in. But then you go one step back and then say, well, I'll set now L to be n minus 1. So then this will be Jn minus 1 of in minus 1, which will be the minimum over all actions un minus 1 that are feasible in state in minus 1 of the expected value of the sum of this single stage cost in stage n minus 1. So which is x k of xn minus 1 comma un minus 1 comma xn. And then plus Jn of xn. Now Jn of xn, I know is h of xn. Okay, so I'll just plug that in. And then you can see that, well, this is nothing but this essentially, this is just an expansion of what this expectation is. These are what we call as transition probabilities. Probability of going from state I to state J or state IL to state J when action UL is chosen in state IL. I mean, that's sort of compactly represented in this using this notation. So the point is that, if UL star is something that minimizes the right hand side above, and we associate mu L star of IL as identify this with UL star, then we know that this policy pi star, which is obtained as mu 0 star, mu 1 star up to mu n minus 1 star, that would be optimal. Is there any question till now? Okay, so maybe we can move forward. So next, what I'll do is I'll just give you a quick example of a control of a queue. I mean, I told you earlier that I am taking some of this material from Bertsikas's volumes. This is, I think, volume 1 or 2. I don't remember. I think probably volume 1. So this example, okay. So what does it do? I mean, so what this example says is the following: there is a single queue. So there's this buffer wherein, if packets arrive into this buffer, they will wait for their turn, and they are sort of served in a first come first serve basis. Now it's assumed that it's a discrete time queue, so it's essentially packets can arrive at any one of these instants, 0, 1, 2, and so on, and it evolves up to time capital N. Okay. Let me show this. Okay, so let's assume that, as I said, the arrivals and also departures are at discrete instants. We'll assume that, only one customer can be served during a period, and moreover, a customer in service can take multiple periods for its service. Okay, so it's not necessary that a customer who gets into service at time, let's say time I or time 1 gets out of service at time 2. It may or may not happen. A customer will enter service at time 1 or 2 or 3 and so on, but then it may not get out at time at the next instant. It may take multiple instants to get out. Okay, so that is possible. We'll assume that there are two types of service that are available. There's a fast service which comes, which we denote as UF, which is the action standing for that. And then there is a slow service which stands, whose action we denote as US. Let's assume that the fast service comes at a cost of CF per period. The slow service comes at a cost of CS per period. Well, quite obviously, I mean, it's natural to assume that CF is more than CS. I mean, if you want a faster service, you pay more. So that would be a natural assumption. Now let's assume that, PM is the probability of M arrivals during a period. And, let's also assume that when you are using fast service, the customer in service at the beginning of a period will finish service by the end of the period with probability QF. And this is independent of the number of periods that a customer has been in service for and the number of customers that are already there in the system. And when you are correspondingly using a slow service, then the customer in service gets out with this probability QS at the end of the service, at the end of the period. And we'll assume again that QF is more than QS because you are paying more. So the probability that you will be out of the system by the end of the period is higher as opposed to, when you use a slower service. So let's assume that if there's a holding cost. So suppose there is this cost that you incur if there are IE customers that are already there in the system. And at time capital N, I told you that everything terminates. So this capital R of I, let's say this is the terminal cost that you incur if there are I customers that are there in the system. Now, if you were to actually find out what these transition probabilities corresponding to each one of these situations is, I mean, there's a long description that you'll have to write down. I mean, so if you are in state 0, which means you are in an empty system at time 0, and at the next instant you find that there are j customers, and this j could be anything from 0, 1 up to n minus 1, then the probability under whether you are using the fast service, well, it makes no sense to have the fast service or slow service because there's no one there. Okay, so this probability is simply pj, okay, which is the probability of j arrivals into your system. On the other hand, if you see that at the end of the system, end of the time period, at the very next instant, that is, you see n customers, then it could have happened that n customers actually arrived, or n plus 1 arrived and 1 had to leave because the buffer size is n, or n plus 2 arrived and 2 had to leave because the buffer size is n, and so on. So in general, it could be the sum of over m equals n to infinity of pm. And so you can actually derive all of this. It's one thing that I wanted to also write this out is because, when we talk of Markov decision process, in general, solving solution techniques for Markov decision process would rely invariably on what we call as a system model that is specified via these transition probabilities. So invariably, you will have to find out what the transition probabilities are if you were to solve for the Markov decision process. Later on, we'll see what are some of the ways in which you can, get rid of this situation, largely using stochastic approximation, where you assume you don't know what the transition probabilities are. You just have access to data, and then the question is, what do you do with that? Okay, continuing with this example. So the single stage cost in this case would be R of I, which is the holding cost for I customers, plus CF if you were to use fast service. Alternatively, R of I plus CS if you were to use slow service. That would be the single stage cost. And if you write down the dynamic programming algorithm that I described a couple of slides back, this is what it will be, that Jn of I is R of I. Jn of I is like the terminal cost, the final function. Okay, so that's just corresponds to the terminal cost R of I, capital R of I. And then in any of the previous stages, so you will find that Jk of I is the minimum over two terms, one term corresponding to the fast service, the other term corresponding to the slow service. You take the minimum term by term and then make a decision on, what is the best option here, whether it is the fast service to use in stage n-1, or is it the slow service in n-1. Likewise, you go then, once you have decided what it is, then you know what Jn-1 of I would be. Then you go one step back to find Jn-2 of I, wherein, so Jn-1 would then be used here instead of Jk plus, because k plus 1 would then be n-1, because k is n-2 then. And so this, if you go recursively backwards, essentially you can find this entire sequence of functions, Jn, Jn-1, Jn-2, all the way up to J0. And this is what it is. There's this other class of functions that other class of long-term objectives that we call as a stochastic shortest path problems. So here, the time horizon is finite, but it's random. Okay, so in general, it's not something that is set a priori. So termination happens whenever you are in a certain state. Many times we also call that as the goal state. And of course, it's not necessary that you have a single goal state. You can have multiple goal states or a set of goal states and so on. So termination happens when you reach that set, and quite obviously because the process evolution is quite random. There are on different trajectories, you will hit the goal state at different times. So in general, you cannot say, you cannot specify a time precisely as to when that goal state will be reached. But you can, that of course under some conditions you can assume that the goal state will be reached in a finite time, even though the time is random. So in this situation, it makes sense to talk about what we call as stationary policies. There are two ways in which one can specify a stationary policy. There is what we call as a stationary deterministic policy. This is one in which you recall what we called as pi is this vector of mu0, mu1, mu2. Of course, in the finite horizon setting, we ended at mu(n minus 1). If it is uh, like a stochastic shortest path problem, as we are considering, you cannot specify what n is. So let's say this is this setting where pi is mu0, mu1, mu2, and so on until you terminate. Now it makes sense, as I said, to think of stationary policies. By a stationary policy, I would mean that all of these functions mu I are the same as mu. Okay, you are not really changing the function from time to time. You're just playing according to a given function. And many times we'll call this mu function itself as an SDP, or a stationary deterministic policy. And likewise, one can also describe what we call as a stationary randomized policy. So this instead of saying that I'll specify one particular action with a given state, I can say that I specify a distribution over actions. Okay, so that distribution is specified by phi of I comma A, where A is an A of I. A of I, as I said, is the set of feasible actions in state I. So once you specify this distribution, and that distribution, this is distribution that is specific to state I over the actions that are available. And that would constitute, the stationary randomized policy. Now, it can be shown that the optimal policy here is a special stationary policy, and these policies are what we call as proper policies. I will come to that. Now here the basic setting is the following. So let's assume that state space is the set of states is this set 0, 1 up to n, where 1 to n are non-terminal states. So if you are in any one of these states 1 to n, then the process evolution continues, while 0 is what we call as a terminal state. If the process hits 0 state at some time, then the process evolution stops therein. Okay, so let's assume that the single stage cost is denoted in this manner, that is G of SAS prime. Suppose S is the state at the current instant. A is the action that we choose now, and S prime would then be the state at the next instant, very next instant. Okay, and so the cost to go vector under policy mu, let's assume the call that as J mu. So this will be defined in this manner, that J mu of I is the expectation over sum from t equals 0 to capital T minus 1 of the sum of all these single stage costs, given that we are starting off in state I. Now again, note that capital T, as I said, is the termination instant. It's not fixed, it's not finite. I mean, it is finite, even though it's not deterministic, it is a random instant. Okay. So the goal here is to find, an optimal cost vector J star, where J star of S is the minimum over all mu. Mu is again these are functions from states to actions of J mu of S. So that's ultimately the goal that we have. Now this problem, as I said, is hard because T is random. T is finite, even though it is finite, it is still random. So we describe a couple of operators. Let's call T and T mu. So these are operators that map R power mod S. So think of this as the state of set of all functions from the state space to the real line. And if you input any function from the state space to the real line, what you get as output is again a function from the state space to the real line. And these are obtained in this manner. So for all these non-terminal states, 1 to n, we'll define T mu J of I as this quantity, where note that it is the sum of the expected single stage cost when you pick actions according to mu I plus J of J. Okay, this capital J is basically this capital J. Okay, so that's what it is. So, and likewise Tj of I. Now in Tj of I, we don't have a mu. We are not specifying a policy mu according to which actions are chosen. So we look at all of these. So sum over J equals 1 to n of P of J given A, A comma I, where A is a feasible action in state I. So we look at all possible feasible actions that are there and then take the minimum over A, okay, of all of these, of this entire thing. So we'll call this as Tj, okay. Now T mu J, as I said, it can be viewed as the cost to go vector for a single stage problem or a one stage, finite horizon problem. When the terminal cost is like, sorry about that, I don't know what has happened. Give me a second. Okay. Something's happening. Sorry. Yeah, okay. So T mu j can be viewed, as the cost to go vector for a single stage problem when the terminal cost is j and the policy is mu. Okay. And likewise, you can view Tj as the optimal cost to go vector. So it's not the cost to go vector under a given policy, it's the optimal cost to go vector. This is for a single stage problem that has a single stage cost g, and let's say the terminal cost is j. Now it turns out that T and T mu are what we call as contraction mappings. So this is a definition of a contraction mapping. So let's assume that capital U is some Banach space. By Banach space, what we mean that it's a complete normed vector space. So an operator T defined, T is in general, and it's some operator, and so T mu could have also have been that operator. So in general, an operator T from U to U map takes in an element from the Banach space, gives you another element in return in the same Banach space. So there is a contraction mapping if there exists a lambda lying between 0 and 1, less than 1 clearly, such that norm difference of TV minus TU is upper bounded by lambda into norm V minus U, and this should hold for all U and V in U. Now there's this result, there's a very popular result that goes under the name of Banach fixed point theorem. And what it says is that, let's say U is a Banach space and T is a map from U to U, this is a contraction mapping. Then there exists a unique V star such that TV star is V star. So this is V star is basically what we call as a fixed point of this operator T. And moreover, if you start from any V0, pick any point V0 in U, then you obtain this sequence Vn that is derived in this manner, that Vn plus 1 is Tvn. So you start from V0, you get V1 by applying this operator T. You plug in V1, you get V2 by applying this operator T on V1, and so on, which in general will be Tn plus 1 of V0. This would, as n goes to infinity, this will converge to V star, which is the unique fixed point of this operator T. This is something that we will make use of as far as these operators T and T mu are concerned. So here is, I told you earlier that we are going to be looking at a special class of stationary policies. And this is that class of policies that we are going to be talking about. There is this, these policies that are called as proper policies. So a stationary policy mu is said to be proper if, when using this policy, there is a positive probability that the termination state will be reached after at most n stages, regardless of the initial state. So this n is basically the same as the number of states. Okay. So a stationary policy, again, let's look at it. So a stationary policy mu is said to be proper if, when you are using this policy, there is a positive probability that the termination state will be reached after at most n stages, which essentially means that if you look at probability of Sn being not equal to 0, 0 is our terminal state, given that the initial state is I and I is a non-terminal state, and you are following this policy mu, and you take the maximum over all of these, I equals 1 to n, over the non-terminal states, this should be less than 1. Okay, so rho mu, let's say, is that. So stationary policy, if this happens, then we say that mu is a stationary policy. Mu is a proper policy. So a stationary policy that is not proper, we'll call that as an improper policy. And the basic underlying assumption here is that there exists at least one proper policy. And moreover, for every improper policy mu, J mu of I will be infinity for at least one state I. Okay, so again, what is J mu of I? J mu of I is the cost to go function under policy mu. Okay, so that is what we call as the value function under policy mu. Now it turns out that if we look at any of these vectors, let's say J and J prime, such that J is less than or equal to J prime, then this would mean that Tj is less than or equal to Tj prime. you can see that, and likewise T mu j is less than or equal to T mu j prime. And this is easy to see from the definition of these of the Bellman operators, I mean the T operator and the T mu operator that we had defined. It also turns out that the optimal cost to go vector, which is J star, satisfies this equation, okay, which is nothing but J star is Tj star. In other words, J star is the unique fixed point of this operator T. So it turns out that, you know, T and T mu, these operators that we have are basically they are contraction maps. You can show that they are contraction maps. And therefore, by the Banach fixed point theorem, they will have a unique fixed point. And those the unique fixed point for operator T is what we call as J star. The unique fixed point for operator T mu is what we call as J mu. Okay. So there is a typo here. This should have been T mu. I now see it that there is a problem. I meant T mu here. It's not T. Because here it should be T. Here it should be T mu. Okay, so what does this equation say? What this equation says is that J star of I, which is the optimal cost to go from state I, is the minimum over all actions U of the sum of the expected single stage cost, right? Plus the cost to go from the next stage onwards. Okay, so if you see yourself in state J at the next instant, so you ask the question, what is the cost to go from the next state? If I knew that, then if I plug this in and take the minimum overall actions U, I should get J star of I. So that is what this Bellman equation tells us. Likewise, the Bellman equation for a given policy mu gives us this, that J mu of I is the sum over J in S of Pi J U. So the minimum is gone, but instead of U, you have, again, there's a problem. Sorry about this. So this U should have been mu of I actually. Yeah. Okay, sorry about this again. So this U is actually mu of I. So that's the particular action that you are choosing here. Okay, so again, this U should be mu of I as well. So which means that the action that you choose in state I is guided by the policy mu. Okay. And then you get into a next state. And so this is the single stage cost that you incur. And then you ask what is the cost to go from the next state onwards, which is J. Okay, so this equation will be satisfied. And it turns out that J star and respectively J mu are the only solutions to the Bellman equation, correspondingly the Bellman equation for this given policy mu. Because as I said, they turn out to be, you know, contraction operators. And so here is a numerical scheme for actually evaluating so what we call what the optimal value functions. So this is what this goes under the name of value iteration. So what it says is basically follow the same approach as was given in the Banach fixed point theorem. You start off with an initial vectors J, which is a map from S to R. For instance, and moreover, you should set J of 0 to be 0 because 0 is your terminal state. Okay. For all the non-terminal states, you can set them arbitrarily. I mean, for instance, you could even set them to 0. I mean, J of 0 initial values. J of 0 is anyway 0, but J of I could have been 0 as well for all I that are not equal to 0. And then what you do is obtain the sequence of vectors. Start with J. J is something that you decide. And then Tj, T square J, T applied on Tj, which we call as T square J. Then T power 3J and so on. And in general, T raised to Kj will be obtained from T raised to K minus 1J using this operation. And if you do this, then as K goes to infinity, one can actually show that Tkj will actually converge to J star, which is the optimal cost to go and which is the solution to the Bellman equation, which is the unique fixed point of the Bellman operator. Okay, likewise, one can show that if you hold your policy, yes, you can do this similar thing for the operator T mu. Now it turns out that the optimal policy mu is the one that satisfies the T mu of J star is Tj star. Okay, this is the policy that achieves the minimum in the Bellman equation. Okay, so that's essentially what it is. There's another related scheme which goes under the name of policy iteration. It's actually a two-loop process. So it goes via two nested loops. There's an outer loop and then there's an inner loop. The outer loop actually updates the policy and then there's an inner loop, which updates the value function corresponding to the given policy. So what you do here is that instead of starting from a given estimate of the value function, which was the procedures adopted in the value iteration process, right, value iteration algorithm, we start with a given policy. You start off with an arbitrary choice, mu0 of policies. Uh, and for instance, if you don't have a very clear idea of what might be a good initial policy, you might take it to be the completely random policy, which means you pick all actions with the equal probability, or which essentially means you pick actions according to the uniform distribution. That's one possibility. Okay, so you can start off in that manner. But then what you do is you generate a sequence of policies, mu1, mu2, mu3, and so on, by first going into the inner loop. So once you have selected an arbitrary policy, you get into this inner loop, where we actually solve for the given policy, find the corresponding value for that given policy. So once you have decided on mu0, you find what j mu0 would be, okay, by essentially doing a value iteration type of schema inside. Or alternatively, you can actually, one can see that you can directly compute this. If you know that transition probability matrix is something you know, but then you will need to compute the inverse of this matrix, I minus gamma p. Okay, if you do this, then if you multiply this, multiply this by the vector of single stage cost, then that would give you j mu k, which is like the value function under policy mu k. Okay. But if this is difficult, if finding this I minus gamma p inverse is difficult, for instance, it could be the case, when the number of states is very large, then you could use, as I said, value iteration type of a procedure, wherein you know what policy mu k has been suggested by the outer loop. And you start off with some initial estimate of the value function there, and then keep on iterating. So you have t mu k j, and then t mu k j, and t mu squares, t mu k squares j, t mu k cube j, and so on. And then this sequence that you obtain would converge to j mu k eventually. And once this converges, what you do is, you come out of this loop, get into the outer loop, and do what we call as a policy improvement step. So here what you do is you find a new policy, let's call that as mu k plus 1. And that is obtained in this manner. As I said, you look at the policy mu k plus 1 that achieves the maximum, or rather the minimum in this case, of tj mu k, the optimizer, okay, the optimizing policy over this. Okay, let's identify that as mu k plus 1. So that is basically the policy improvement procedure. And so it can be shown that the policy iteration algorithm, which involves this procedure, this two loop procedure, generates actually a sequence of policies mu k. And this would be such that at any instant you are guaranteed improvement. J mu k plus 1 will be less than or equal to j mu k till the time you converge. When you converge, of course, then j mu k plus 1 will be the same as j mu k. It does not mean that the policies will be the same. I mean, the point is you can have multiple optimal policies, but all of them would give you the same cost, right? Because they are all optimal. So that's what it is. I mean, so you may converge to different, so you can find different policies that are optimal. But again, as I said, all of them would lead to the same cost. Okay, so j mu k. So once you see that j mu k plus 1 is the same as j mu k, you can terminate your procedure, and then you know what the optimal value function is. Okay, so that's what it is. The next class of next class of approaches goes under the name of what we call as infinite horizon discounted cost problems. So here the number of stages is infinite, and what we'll do is we define an admissible policy phi to be a sequence of functions mu0, mu1, and so on, such that mu(n) again is a map from S to A. And then the goal is to look at this infinite horizon. I mean, we are no longer in a setting where the horizon is finite, or it could be finite and deterministic, or finite and random. We are now in a purely continuous, purely infinite horizon setting. These problems are also go under the name of what we call as continuing problems. Okay, they don't end. The previous set of problems go under the name of what we call as episodic problems. Okay, so they go via termination into a goal state kind of thing. So here the goal is that you want to find an optimal policy pi star that minimizes the cost to go, which is like the sum over all j equals 0 to infinity of this whole thing. Okay, so the single stage costs are weighted by this discount factor. So at time 0, you don't give any weight. Gamma power 0 is 1. Then at time 1, when you are at the next instant, you assign a weight of gamma. At the next instant, you assign a weight of gamma square, and so on. You can see that since gamma is something that is less than 1, the weights that you assign subsequently are going to carry less weightage in terms of the overall cost structure, as opposed to the cost that you incur in the immediate future, okay, currently or in the immediate future. So in many ways, this setting is more catered towards what we call, I mean, it would be more catered towards a transient sort of setting where you care more about what you are going to achieve in the immediate future, as opposed to what you are going to look far into the future. I mean, so it makes you more short-sighted in some sense. But of course, as you can see, the amount of the window of length that you look for will be guided by the gamma. And gamma plays a crucial role. For instance, compare two situations, one where gamma is like 0.1 or 0.01, which is a very small quantity, and contrast it with gamma equals 0.99 or 0.999. As you can see, if gamma is very close to 0, then you are really more worried about what you are going to gain right now, as opposed to what you are going to gain maybe 10 instants from now, or maybe 20 instants from now. So again, by a suitable choice of gamma, you can sort of play with your horizon length that you really care about. Now it turns out that we need gamma in order to ensure that these costs are bounded. And so, for instance, if you assume that the single stage costs are all bounded by some number capital M, and you can see that this j pi of I would be upper bounded by M by 1 minus gamma, which is finite. Then it would really make sense to ask the question, what is the optimal policy? For instance, that would not have made much sense if you had gamma to be equal to 1, which would essentially, and let's say you are in a situation where the sum of all of these is infinite. So whatever policy you use, it's still an infinite cost. So the question is, what do you optimize over? So it makes sense to have this gamma for that very reason, that it ensures that these costs are bounded, and therefore now you can ask the question, can we find the optimal policy? One can similarly define these operators T and T mu in a similar manner as before, except that there's this gamma multiplying. Earlier in the shortest path problem, you didn't have this gamma multiplying j of j here. Now you have this gamma, so you are looking at the gamma times the cost to go for the next stage. So that's what it is. Okay, so now when we look at these operators T and T mu, so it turns out that for any bounded function j, j star of I is the limit as n goes to infinity of t raised to n j of I. So if you start with any j and you keep on iterating j t squares j and so on, you get j star of I. Similarly, you start with any j and you go on updating via t mu as j t mu squares, j t mu cube j and so on. This entire sequence will converge to j mu of I. Okay, so essentially there's an important result. And then there is the Bellman equation of optimality in this case as well, which is like the unique fixed point of this operator T. And likewise, there is a unique fixed point of this operator T mu, which is the Bellman equation corresponding to a given policy mu. Okay, so it turns out that J star and J mu are respectively the unique solutions to the Bellman equation, as well as the Bellman equation for a given policy mu within the class of bounded functions. Now here is a necessary and sufficient condition for optimality. So we say that a stationary policy mu is optimal if and only if mu of I attains the minimum in the Bellman equation for every state I, which essentially means that Tj star is T mu J star. So this is like the sufficient condition. So it is easy to see. So let's assume that this condition holds. So Tj star is T mu J star. So then we know that by the Bellman equation, J star is Tj star, but then Tj star is T mu J star. So which means J star is T mu J star. And T mu has a unique fixed point, J mu. Okay, so J star should be equal to J mu, which means mu is the policy that is optimal. On the other hand, suppose mu is optimal, then this would mean that J star, which is the optimal cost, should be achieved by this policy J mu. So which means J star should be equal to J mu. And therefore now we know that J mu is T mu J mu, and therefore J star will be T mu J star because J star is J mu. And T mu J star and J star should satisfy T J star, right? So J star equals T J star. So this essentially means that T mu J star should be T J star. So this condition is both necessary and sufficient to ensure optimality. Again, in this case, one can go via value iteration, wherein you start off with some initial estimate of the function J0 and then go on iterating in this manner. As Jn plus 1 as Tjn, and as n goes to infinity, we know that Jn sequence will converge to J star. Likewise, you can iterate with respect to this operator T mu, which is again a contraction, and therefore Wn, if you obtain Wn plus 1 as T mu Wn, then the sequence Wn will converge to J mu as n goes to infinity. Okay, so this is a key result based on which value policy iteration is based. Essentially, this is the same thing that we talked about. That T mu bar of J mu is the same as T of J mu. Essentially, if that happens, then J mu bar should be less than or equal to J mu. And then policy iteration is again a procedure that sort of is similar to exactly the way in which we described policy iteration in the stochastic shortest path case, wherein you start off with an initial policy and then get into the loop, inner loop where you do policy evaluation and then come out of that loop, do a policy improvement. And then, once you have done policy improvement, go back into this loop to do policy evaluation, then come out, do an improvement one more time and go back and repeat this process. And ultimately, we know it will converge. Okay, so it will converge to the optimal policy. And corresponding to the optimal policy, we'll have the optimal cost to go. Okay, so here is an example which I have taken from Richard Sutton's book. So let's say we have a mobile robot that is there in an office environment, and in an office setting there are various people on various desks sitting around, working on their laptops or whatever. And what they are doing is let's say they have taken some soft drink cans and so on, and they just use the cans and then they left it on the table. And the job of this robot is to either actively go around looking for empty cans and then it picks the cans and drops it into its bin that is there, moving with it. Or alternatively, it will stand in some place and assume that the office people are generous enough, they will come, maybe some of them will, they will come and drop the cans into its bin. Okay, so there are now these two actions that it needs to decide on, whether to actively search for empty cans by moving around, or else stand in a corner and let people come and drop cans in its bin. Now the state of the robot is it could be either high or low, denoting the charge level. Now it's a mobile robot, so if it does an active search by moving around, its battery will get depleted. And somehow, if it goes below a certain threshold, then it will have to either go and get itself recharged, or else if it drops dead, then someone will have to take it and get it recharged before it starts acting again. Here is a transition diagram for this robot. So let's say these are two states denoted by these circles, high and low. And the actions that are feasible in these states are these wait action, which means it stands in a corner waiting for people to drop cans, or it can do a search action. Let's assume for simplicity that if it decides to wait, then with probability 1, it will continue to be in the high state. And the reward it receives is RW. On the other hand, if it decides to search, then with probability alpha, it goes back into the high state. And with probability 1 minus alpha, it goes into the low state. The reward in either case is R search. I mean, so of course, this is not something that may be something that is fixed. It could be a random reward that depends on this search action. Okay, so which means that the reward distribution may have been specified. It's just that it could be some random reward it receives depending on this action. On the other hand, if it is in the low state, then it can again decide to search, or it can decide to wait, or it can decide to recharge. If it decides to search it with probability beta, it stays back in the low state. Alternatively, it might drop dead. And if it drops dead, someone will have to lift the robot and put it in connect it to a plug point. Once they do that, then it goes back into the high state. But then if during that process, a cost is incurred. So let's say some -5 is the cost that you incur during this operation. And this happens with probability 1 minus beta. If it is in the low state, then of course it can decide to wait. If it waits, then with probability 1, let's say it stays back in the low state, and the reward is RW. And on the other hand, if it decides to recharge of its own, which means this is the decision taken by the robot that okay, my charge level is low, let me go and recharge my battery. So it will go by itself and connect it to a plug point. So in which case it jumps into the high state at the next instant, and the reward is 0. So all of this can be, as I said, can be described via transition diagram. Of course, many times it's too complicated to draw a transition diagram for everything, because here there are just 2 states and maybe 2 or 3 actions. In general, there will be multiple states and multiple actions and so on. It may be difficult to describe via a transition diagram all of this. But the point is that, well, we can write down the Bellman equation in this case. So there is the value of the high state. You can write, there are 2 actions that are feasible in the high state. There's the search action or the wait action. Corresponding to that, you can write down what the corresponding costs are. Okay, and for likewise for the low state, there is this action. There are 3 actions now that are available. There is the search action, whose cost is essentially this whole thing. There's the wait action whose cost is here, and then there's the recharge action whose cost is this. You need to take the maximum over all of these. Sorry, whose value is this? So let's say this is a maximization problem, wherein you are assigned rewards or the costs. So the value of the low state in the high state. Okay, let me skip the long run average cost setting. I mean, I think this is we have kind of run out of time. In any case, let me just tell you this, that there are these limitations of numerical methods or exact schemes. One of the key limitations is that in order to solve the Bellman optimality equations using numerical techniques, one requires the complete knowledge of transition probabilities, or these transition probabilities. I mean, what is the probability of going from state I to state J when you have picked action A? Okay, you need this information entirely for every state action tuple. You need these probabilities, and many times in real life systems you will not have access to this information at all. And moreover, the amount of computation that is required to solve Bellman equation, this actually grows exponentially in the number of states and actions that are there. And therefore, one resorts to approaches that are a combination of simulation of real data and what we call as feature-based approximations. So they involve combinations of both approaches that use that are based on data samples that are made available, and they also make use of approximation approaches. So for instance, if the number of states is so large that you cannot even store a vector of the size of the state space, which is the value function, then you would rather approximate the value function using some parameterized representation and then work in that parameterized class of functions. Because you may represent the value function by a low dimensional parameter, by functions that are functions of a certain low dimensional parameter, and then you can work with sort of those low dimensional objects that may be simpler to use as opposed to working or finding the value function of every single state and so on, which may actually not even be required. Okay, I think we have run out of time, so I'll probably continue in the next class. If there are any questions, we can sort of now take them.
Yeah, I have a couple of questions, if I may.
Yes, yes.
Yeah, so you describe this control Markov property,
Correct.
and you define it in terms of probabilities. So
Yes.
I have one question. What is the probability measure that one uses here? And the reason I ask this question, because there are some treatments where, if you have a policy, then that gives rise to a measure on the set of state action trajectories. So I've never been able to resolve this confusion. What comes first, the measure or the policy?
No, no. So you're talking about, let's say, yeah, the controlled Markov property, right?
Yes, this one, yes.
No, so yeah, I mean, so we are, as I said, we are in a setting which comprises of discrete states, discrete actions, and of course you can extend it to settings wherein the states and actions take values in continuous sets. Now the point is that the transition probabilities. Okay, so the probability of going from state, let's say S and action A into state S prime is given by this. I mean, that's all I'm saying.
Okay.
Now,
There's also the other equality that, the first one. Right here.
okay.
Which is the conditioning on the whole previous trajectory is not
Correct.
giving any additional information. Yeah.
Yes, yes.
Okay.
Okay.
That's fine. So so you had this definition of a proper policy where you require the probability of converging to that target state within
Yes.
an at most n states. So is that at most n required, or what happens if you just say that it has to eventually reach, or are the two equivalent in the finite state case?
No, I believe they are equivalent. See, the point is that suppose you are, you are in any of these non-terminal states, and you ask the question, what is the probability of, terminating from any of these states? So if you are asking the question, well, you start off in state I, and you are continuing to follow policy mu. And then the question is, what is the probability that you still have not terminated after n steps? Because you have completed this entire thing that you have looked at n steps of the thing, and it turns out that if you uh, yeah, I mean, okay, so what this is saying is that if you start off from any state in n steps, you should actually, in at most n steps, you should actually terminate with a positive probability. I mean, so the thing is that if you so there is still a probability of non-termination.
Yeah.
And that probability is 1 minus of that.
Okay.
Correct.
Okay. Okay. A last question. So I have seen treatments which say that the stochastic shortest path problem can be absorbed into the infinite horizon problem. By just letting the target state or be an absorbing state with zero reward or something else. So what exactly is the difference? So you describe the value iteration and the policy iteration techniques for both the stochastic shortest path and the infinite horizon case. So is there any difference between them, or what is the difference when it comes to the methods?
Yeah, and when it comes to the methods, no, you are right. I mean, so the point is that the finite horizon problem can also be described by a stochastic shortest path, and vice versa. And moreover, the stochastic shortest path problem can be cast as an infinite horizon discounted cost problem as well, where the discount factor comes because of this rho mu thing. See, the point is that you have this gamma power j, instead of that you get rho mu power something, and that comes in naturally. I mean, one can actually visualize that and see that you can cast it everything, then it becomes actually analogous to the infinite horizon problem as well. Now
Yeah,
yeah, you had actually, I didn't get your first
yeah.
part.
I realized I missed the discounting factor. So in the stochastic shortest path, there was no discounting factor. In the other case, there is. So
Yes,
yeah, I got the answer to my question. Yeah, sorry. It was not a good question to ask. Thanks.
Thanks. Yes, any other questions? Okay, so if there are no other questions, maybe we can possibly stop here, and then we'll meet again, I think tomorrow at 11:30, if that is fine.
Yeah, that's correct.
Okay. Okay, thank you all. Thanks for coming.
Yeah, thanks.
Yeah, thanks.